Welcome to the Intel FPGA online training Introduction to Hyper-Retiming. My name is Marlon Price and I will be the presenter for this training. To understand how your design can reach the highest speeds in the Hyperflex architecture, you really need to know how Hyper-Retiming works. That is the purpose of this training. So upon completion, you will be able to describe Hyper-Retiming and how it improves design performance in devices with the Hyperflex architecture, such as the Intel Agilex and Intel Stratix 10 FPGAs. To do this, we will start by defining Hyper-Retiming and what differentiates it from conventional retiming methods. We will end with a discussion of how Hyper-Retiming works in the Intel Quartus Prime Pro software. So what exactly is Hyper-Retiming? Retiming is a well-known optimization technique that can significantly improve design performance by repositioning the registers in a path to balance the delays between them. While adding more delay to shorter paths, it also reduces delays in longer paths. Since performance is determined by the longest delay path, retiming translates to faster clock speeds. The example on this slide demonstrates this. In the upper example, retiming is performed by moving registers backwards through the design. In the lower example, the registers are moved forward. But in both cases, the maximum combinational delay between registers was 2 lookup tables in length, and it is now 1 lookup table in length after retiming. So with half of the delay between the 2 registers removed or repositioned, the design can essentially run at twice the speed. This performance increase is done without any change in design functionality or any additional latency. In all examples on this slide, it still takes 3 clock cycles to go from input to output regardless of the positioning of the registers. Retiming can be performed manually in HDL, but it is difficult to do because a designer must figure out which registers should be moved and where to place them. Then the designer must recode their logic to implement those changes. This requires in-depth knowledge of synthesis techniques and of the target FPGA architecture. A better solution is to use automated retiming. In the Quartus software, there are 2 types of automated retiming: retiming performed as part of physical synthesis and hyper-retiming. They are both on by default. Even though physical synthesis retiming results in a performance gain, that performance gain is achieved using registers found in ALMs. The challenge with this is the ALM register locations are very coarse-grained since they are in specific locations in the device. Remember too from the Hyperflex architecture overview online training that there are timing delays associated with getting to and from an ALM register. This challenge is illustrated in the diagram on this slide. In the path at the top, you can see that due to the layout, there is an imbalance in the delays: 1.5 nanoseconds on the left register to register path and 3.5 nanoseconds on the right. To retime this path, we would want to move the middle register to another location into a separate ALM. The difficulty now is finding an ALM that is available to use and that sits in the ideal location for balancing this path. So in the path at the bottom, you can see that a location has been found, but because of the location of the ALM and the delays into and out of it, the retiming does not ideally balance the delays. We are left with 3 and 2.5 nanosecond paths. So while the performance has increased by 16%, there is still room for further increase. And this is just one path. Imagine having to do the same retiming on a 256-bit bus and across 8 or 9 stages of registers. So although effective for increasing performance, conventional register retiming can still be very challenging for the place and route tool. First, additional logic and routing resources are required. Unused logic cells must be available near the circuit that needs to be retimed. If a wide bus has to be retimed, this will require a large number of additional logic cells to do that retiming. This may or may not be possible depending on how fully utilized the device is. Furthermore, the additional logic and routing resources add extra delay. This added delay opposes the effectiveness of retiming and its performance increase. Finally, depending on when in the compilation flow the retiming is performed, the placement and routing may have to be redone to include these newly added logic cells in the path. In a conventional architecture, it might take multiple iterations and complex algorithms to find register resources in the most useful locations. Note, some tools do retiming in the synthesis stage, where the synthesis tool detects potential imbalances and retimes, so the place and route tool only places the retimed netlist. This can save greatly on compilation time over retiming the design after placement and routing, but there is guesswork being done here, as the synthesis tool does not have the actual path delays from the placement to completely decide where the registers should be repositioned. Hyper-retiming is retiming that is performed by utilizing the hyper registers found in the Intel Hyperflex architecture. Hyper-retiming is accomplished by bypassing an ALM register and enabling a hyper register instead. Thus it looks as if the ALM registers are being pulled or pushed into hyper register locations. Hyper-retiming is performed automatically by the Quartus Prime Pro software on designs targeting the Hyperflex architecture. There is another aspect to hyper-retiming that refers to the process of eliminating structures in your design that serve as barriers to more effective hyper-retiming. We'll cover that in follow-up training to this one. Now, let's look at that same path as before, but being implemented in the Hyperflex architecture. We can now see that the path was retimed by moving the register out of the ALM and into the interconnect. In other words, we use one of the many hyperregisters in the interconnect to retime the circuit instead of another ALM. Since there are hyperregisters located in the routing segments, there are many options for register locations to choose from in the row and column interconnects between the two logic cells. This allows the tools to optimize the retiming by choosing the hyperregister that best balances the delays in the circuit. So now in our circuit, we see that the hyperregister has successfully balanced the register-to-register timing paths to 2.5 nanoseconds on each side. A 2.5 nanosecond delay translates to 400 megahertz or a 40% gain in performance. There are three key advantages of hyper-retiming over conventional retiming. Hyper-retiming is done after place and route, so large-scale, time-consuming changes to the placement and routing are not required. The performance increase with hyper-retiming compared to conventional retiming is higher because the fine-grained location of the hyperregisters in the FPGA allows the tools to optimally balance the circuit delays. And 3, the hyper-retiming does not require additional logic cells, so there is no increase in the amount of logic cells used. Hyperregisters are already in the interconnect, so no additional delay is incurred to route to the hyperregisters. This is not to say the ALM registers and physical synthesis retiming do not have a place in optimizing for performance. They most certainly do. But an important strategy in achieving the highest performance possible in devices with the Hyperflex architecture is designing for the use of hyperregisters. Next, let's see how the hyper-retiming process works. Hyper-retiming is performed after place and route, once all the logic is placed and all the timing delays are determined. Since routing channels and block inputs have hyperregisters that can be enabled or bypassed, the existing route chosen by the fitter connecting two blocks can be used just as is. The path does not have to be rerouted to include hyperregisters. Hyper-retiming just has to pick which registers along the path it wants to use and which ones it will continue to bypass. Using the process we see in the next few slides, Hyper-retiming can make very good decisions on enabling hyperregisters without the problems of delay prediction, congestion prediction, and so on that come with fitter algorithms and conventional retiming. Because of the way the Intel Hyperflex architecture is constructed, hyper-retiming comes down to a constraint problem. This greatly simplifies the retiming process. With standard place and route algorithms, the compiler uses heuristics to come up with a solution in a reasonable amount of time. Since the number of possible layouts in the chip is near infinite, the compiler must resolve to what is deemed to be a good enough solution. But this can still take a considerable amount of time, and the solution may still not meet timing. This is a known challenge of place and route algorithms. With hyper-retiming, since the place and route is already finished, the solution space is much smaller. Given a specific set of constraints, the software just finds the best set of possible retiming moves for a given set of paths. The goal is to find a set of registers along the given path or paths that optimize for clock speed. Because of this, the device itself, structures in your design logic, and your design requirements become the limiting factor, not the software. In order to find a solution, the Hyper-Retimer tries to meet a set of constraints governing each path. These constraints ensure that setup time between registers is met. This ensures registers are not too far apart. Hold time between registers is met, which ensures registers are not too close. The design must remain functionally equivalent, so the number of registers in the path must remain the same as the original unretimed circuit. There are valid available register locations for use, and the software must make sure that registers with restrictions that cannot be moved remain untouched. With these constraints, the Hyper-Retimer solver produces a solution that uses a series of retiming moves to optimize for clock performance, thus determining which registers are enabled and which are not. If this solver fails on a particular path, the path becomes what is called a critical chain. We'll talk more about this in follow-up online training to this one. This example path has 2 registers enabled and 4 registers being bypassed. To retime, the Hyper-Retimer is tasked with coming up with a solution that has registers separated by no more than 3 spaces for setup and no less than 1 for hold. To maintain functionality, the solution must still only have 2 registers in the path. Here's an example of one potential solution from the Hyper-Retimer satisfying all constraints. In this solution, B is left alone, C is disabled, and D is enabled. Is this the only solution here? No. But none of the other solutions offer any real advantage over this one. Now let's say we want to run the design faster. To do so, the registers must now be separated by less than 2 delay units. Well, then there is no possible solution while still only enabling 2 registers in the path. The critical chain in the Hyper-Retimer then is the path for which the Hyper-Retimer could not produce a solution for a given set of constraints. In other words, for a target performance level, it was simply not possible for the Hyper-Retimer to place registers in the way that the design needs. Because the Hyper-Retimer knows which constraint in the critical chain caused the retiming to fail, it can provide feedback to you on the reason or reasons a solution was not found and provide recommended design changes to fix the critical chain and improve design performance. Again, more information on critical chains, such as the types of critical chains and potential solutions for critical chains, are covered in follow-up online training to this one. This concludes our introduction to hyper-retiming. In this training, we learned how hyper-retiming involves moving existing registers from ALMs into optimal hyper-register locations to improve overall path timing. It is performed automatically on designs targeting the Hyperflex architecture after place and route for maximum performance gain. Intel FPGA provides many self-help resources when you need design assistance. For example, there are web pages called landing pages dedicated to specific FPGA technology like transceivers, DSP, OpenCL, and high-speed gigabit interfaces. There is a community forum, and there are hundreds of training courses available just like this one. One last thing, when you register for this training, a link was sent to you in your confirmation email that links to a short online survey. Please complete the survey to let us know what you think of this training and if you can think of ways in which it can be improved. This concludes this online training. Again, my name is Marlon Price. Thank you for your time.